Okay, let's dive into this. Welcome to the Explainer. Today we're going to completely demystify large language models. Seriously, whether you're an aspiring generative AI engineer, a Python developer, or just a student trying to wrap your head around what actually powers things like ChatGPT and Gemini, you are in the exact right place. We're going to break this whole thing down, starting from high-level, intuitive concepts, and then we'll work our way all the way down into the actual engineering engine room.
Here's our roadmap for this explainer. First, meet your digital head researcher. Second, inside the transformer architecture. Third, the text generation pipeline. Fourth, prompting, fine-tuning, and RAG. And finally, number 5, the rise of AI agents.
All right, Section 1, meet your digital head researcher. Before we get completely bogged down in the math, the vectors and the matrices, we really need a simple, intuitive mental model for what an LLM actually is. Think of this explainer as a structured masterclass designed specifically for you. So, let's break down the acronym itself, Large Language Model. The absolute most important thing to grasp here is the model part. It's a mathematical system. It is absolutely not just some giant database of everything it's ever read on the internet. Instead, it's a system trained on an enormous amount of data. That's the large part, that literally learns underlying patterns so it can make predictions about human text and code, which is the language part.
And this brilliantly illustrates the difference. Think of a standard older AI model kind of like a digital intern. It can solve basic, isolated functions with very standard inputs and outputs. But an LLM, well, that is your head researcher, because it's been exposed to billions of parameters and just vast oceans of training data. It can hold back and forth conversations, handle incredibly long context windows, and actually understand the why behind your prompts rather than just the literal words you typed.
Section 2, inside the transformer architecture.
Okay, so let's pop the hood of the AI engine and see what makes this head researcher so uniquely capable. Basically, everything changed with this single legendary paper from 2017 called Attention is All You Need by Vaswani and colleagues. Before this came out, older models like RNNs and LSTMs struggled massively with long sequences. They read text strictly sequentially. That meant they practically forgot what happened at the beginning of a paragraph by the time they finally reached the end. The transformer architecture revolutionized natural language processing by totally solving that bottleneck. So, the very first step in this architecture is understanding how the model actually reads. Spoiler alert, it doesn't read words like we do. Inputs are broken down into little pieces called tokens. Think of tokenization kind of like chopping up vegetables before cooking, right? You literally can't make the soup until everything is diced into usable pieces. These tokens are your raw material. Each token is then converted into a numerical vector, which we call an embedding, via a massive lookup table. Essentially, this maps the real semantic meaning of human text into a multidimensional geometric space. Because of this, words with similar meanings end up living right next to each other mathematically. Now, what's really interesting about this slide is the core innovation of the transformer itself, multi-head self-attention. Instead of reading sequentially, one word at a time, the attention mechanism looks at all the tokens in your prompt simultaneously. It calculates how relevant every single word is to every other word. For example, if you have the sentence, "The animal didn't cross the street because it was too tired," the attention mechanism mathematically connects the word "it" directly back to animal, not street. It dynamically captures that context on the fly.
Section 3, the text generation pipeline.
So we have the components now, right? The tokens, the embeddings, the attention mechanism. Let's see how it actually spits out a coherent response. We'll walk through the first half of the data flow. First, you provide a raw text prompt. Instantly, the model's tokenizer chops that text into our tokens. Next, it looks up the numerical embeddings for those tokens. Then, these vectors are fed directly into the stacked layers of the transformer neural network. This whole process is exactly how raw text becomes ingestible, mathematical data.
And here's the second half of that pipeline. Inside those layers, self-attention is applied to really understand the context. Then, the model does its main job. It calculates the statistical probabilities for what the very next possible token should be. Finally, using a specific decoding strategy, maybe that's greedy decoding, which just blindly picks the highest probability, or beam search, which looks a few steps ahead to be safe, it selects the winning token. I really want you to take this away. Despite the billions of parameters, the massive server farms, and all those incredible emergent abilities we see, like reasoning and coding, the core function of an LLM is remarkably simple. It's just a predictive engine driving forward sequentially.
It is quite literally generating the response one single token at a time.
Section 4. Prompting, fine-tuning, and RAG. So the crucial point is knowing how the model works is great, but how do we as developers adapt these massive general-purpose models for specific domain-centric tasks? Well, it all comes down to knowing exactly when to use which tool in your toolkit. Prompt engineering is just manipulating the input text. You're heavily limited by what the model already knows from training. Fine-tuning actually adjusts the internal parameters of the model by training it on a specific dataset. That's great for changing behavior, but it's pretty terrible for adding daily updated facts. And then there's RAG, which provides external context dynamically. Honestly, if you're building enterprise AI today, you absolutely need to know RAG, Retrieval Augmented Generation. Instead of painstakingly retraining the model every single time your company updates a document, RAG converts your private documents into vector embeddings and stores them in a vector database, like FOSS or Pinecone. When a user asks a question, the system searches the database for relevant facts, injects them right into the prompt, and forces the LLM to answer based only on that grounded context. It's the absolute best way to stop an AI from hallucinating and confidently inventing a company policy that just doesn't exist.
Section 5. The rise of AI agents.
Okay, we've talked about how LLMs are engineered today. Now let's look at tomorrow. According to the latest 2025 research from the Gemini Research Institute, generative AI adoption at a partial or fully scaled level has surged to 30% of organizations. To put that into perspective for you, that is a staggering 5-fold increase from just 6% back in 2023. It's moving incredibly fast.
Let's move to and see how this builds across the wider landscape. Across sectors like telecom, consumer products, and high-tech, AI has moved entirely from the fringes right to the forefront. A massive 93% of organizations are now at least exploring, piloting, or enabling Gen AI capabilities. This isn't just an experiment anymore. It is mainstream business infrastructure.
But here is where the evolution gets truly fascinating. 14% of organizations have already implemented AI agents at scale. We're moving away from AI as a simple chatbot tool that just sits there waiting for a prompt, and toward AI as an autonomous team member capable of executing complex, multi-step workflows across completely different software systems. However, with great power comes incredible engineering and operational challenges. Deploying agents at scale isn't just a coding problem, right? 71% of organizations still lack trust in autonomous AI systems. Less than half have established proper governance policies, and there's a worryingly large carbon footprint tied to the massive energy demands of running these foundational models. Fun fact, well, maybe not so fun, training a single major model can emit as much carbon as 5 cars over their entire lifetimes. That's a massive scalability hurdle, and it's definitely compounded by a lack of transparency from the major hyperscalers. Which brings us to the ultimate question for you, the future Gen AI engineers and developers watching this. You now know exactly how the tokens, the embeddings, and the attention mechanisms work. But as these LLMs evolve into truly autonomous agents, are we architecting the right technology, data, and cultural platforms to actually collaborate with them safely and sustainably? I want you to think beyond the code. Thanks so much for joining this explainer. Keep questioning the code.